Good evening to all of you. Myself, Anjali Dixit, and welcome to the third week of the problem solving session, which is conducting for the course of Earthquake Geology, a tool for seismic hazard assessment. So, in this week problem solving session, we'll take few questions and then we'll solve that question by going through the concepts related to it. And also, here we'll discuss a few more extra concepts which will help you to answer the remaining questions related to this week assignment. So, let's take our first question, which says that Dash faces active continental margin, which is characterized by frequent earthquakes and are considered inherently unstable. So here we have majorly four options like Pacific Ocean, Atlantic Ocean, Indian Ocean, and Arctic Ocean. So what are the common point between all these is that they all are oceanic plates. Okay. So let's understand like what would be the correct answer and why. So here, what they are mainly asking that we need to choose which ocean has characterized by frequent earthquake and considered inherently unstable. So since there are earthquakes are frequent, so obviously it would be tectonically active and hence will be unstable. So to understand this, like which region has these characteristics. So here in this image, you can see that it's an image of a world map where all the uh, prominent plates are marked. For example, here we can see the Eurasian plate, which is a continental plate, and another one is joined the Fuca plate, which is marked over here, which is the smallest plate. And apart from this, we have a North American plate, Caribbean plate, and then South American plate, Nazca plate. And I hope you are familiar with this Nazca and the South American plate because this question has been asked in the previous week assignments as well. And other than that, we have an Indo-Australian plate. So these many plates we have. And in the like previous week's session, we have understood the phenomena of like convergent, divergent, or transverse movement or the transform boundary with the like simple example. But now the same thing we are considering using the real example. So whenever the question comes, including the real like plate example, then you'll be able to answer that. So, if we and here this yellow circles that are marked over here and all over this region are denoting the earthquake activity. So you can see that across this region, which is marking a boundary, has a prominent location for earthquake. Now the question comes why it is. So, this answer to this question is that here this boundary is representing. So, since it is a tectonic boundary, so definitely there would be out of three, there would be any movement. For example, it could be a convergent boundary, it could be a divergent boundary, and it could be a transform boundary. So here this boundary marks the convergent boundary, which is denote you can see over here also. So it's a convergent boundary, and where you can see this tooth-like features, it is indicating that this side of plate is overriding and this side of plate of that boundary is it's going down. So for example, if we take the example between the Pacific plate and the Indo-Australian plate, so the Pacific plate is overriding and this Indo-Australian plate is going down to this Pacific plate. Okay. And if we see another example of this NAS, the famous example, that we have studied earlier as well. So is between the Nazca Plate and the South American Plate, where also we can see that this Nazca Plate, so since it's an oceanic plate, so it is going down, and this South American Plate is overriding. And since it's the oceanic and the continental collision, so due to which the landform that we see is the volcanic arc, that is the Andes mountain range. Okay, and other type of phenomena if we want to observe with this image is over here, where we can see that we are able to see the Japanese arc, or the island chain that we see. So that is between the again, it's between the Pacific plate and the Eurasian plate. So here, since it's on the oceanic part, so that's why we are able to see the island kind of features through this entire belt. So here we can see the Aleutian arc, and here we can see the Japanese arc. And also there are another kind of arc as well. It's MBA and CA arc, Cascade arc. So this is the features that we see whenever we encounter the convergent boundary. Now moving further, let's understand what kind of other landform that we can see through the real example, because all those things we have considered in the previous lecture. So this is the same example or the same location. Now this image is highlighting the major trench area. So we have already seen that this whole region is showing the convergent boundary, and that's why there are the frequency of earthquake is very high, and that's why it's an unstable zone, because it is not tectonically stable. And that is the another reason that we called it as a ring of fire, because it is a very active zone. So due to this subduction, we can see the excuse me, trench feature. So these are the major trench that we observe in this entire region, and you can see there are lots of trenches are marked over here. For example, the Japanese Trench, Aleutian Trench, and the Middle American Trench, Peru-Chile Trench, that is between this, where we saw the Andes Range as well, mountain range. And the deepest of among all these trench is the Marianas Trench. So this is the trench feature that we have seen along this ring of fire. Okay, and now I hope you all can answer this particular question. So you all are aware that what ocean or which ocean is highly active. So the answer is the Pacific Ocean, because here we encounter lots of earthquake activity, and uh, it is the characteristic of this Pacific Ocean plate is the subduction. Okay. Now let's understand another concept related to this theme, so it will help you to answer the other questions of the assignment. So other is the sea floor spreading. So far we have understood that what is the convergent boundary, what kind of landforms we can see on that boundary. And now we have also understood that on the real scenario of the globe, that where you can see these convergent boundaries. So the another movement that we have studied is the divergent movement. So let's understand it with this simple schematic diagram. So here's the first phase of this. So earlier, what happens that we called it as an early rifting phase. So due to this, mental plume goes upwelling, and due to this upwelling, since it is a hotter plume, so it tries to make this plate thinner, and also due to this divergent movement, this boundary all further gets thinner. And if this type of motion happens for a long period of time, so we come to the second stage of this rifting that we called as the advanced rifting. And now you can see that this particular region now becomes more thinner as compared to the first stage. And if it is continues like this, that is in the third phase, what we can see is the sea floor spreading. So what is the sea floor spreading when this whole lithospheric plate becomes completely vanished and this mantle plume come on the sea floor to the sea floor. And so since at the sea floor the temperature gets rapidly changed, since it has a more like temperature is, suppose here the temperature is T1 and here is the temperature T2. So we can say that the T2 is more greater than T1 because here we have a oceanic water as well. So since when it comes to the contact of the sea floor, this mantle gets solidified. And due to this solidification, it forms a new crust, and that we call as a new oceanic crust, created at the mid-oceanic or mid-ocean ridge. Now, this mid-ocean ridge is also another kind of landform that we see during the divergent boundary. And why we called it as a mid-ocean ridge? So, since here, these two plates are now completely apart, and here we are getting a, we can see that the new crust is forming. And here, the midpoint of this mantle that will continue continue this upward motion will be at the center of this newly created plate. And it will try to push the older plate in the left and the right direction. And the length of this plate will eventually get increased. So since this mantle will coming at the center of this newly created plate, so that's why we call this mid-oceanic ridge. And since this crust or this plate is an oceanic plate, so that's why this oceanic word is coming. And this whole phenomena is happened in the oceanic oceanic plate divergence only, because in general or generally the divergence boundary can be seen between the oceanic and oceanic plates only. There are few exceptions that we can see this divergent in on the continental plate, but we'll see it later. In general, this divergent phenomena we generally encounter in the case of oceanic plates. So let's move further. So let's see the implication or how the researchers have come up that this is, yeah, like come up with this theory, because there has to be some proof uh, to support this theory. So for this, they do the uh, age mapping of entire globe, and where they have found out a very spectacular phenomena where along this divergent boundary, and this is the very famous divergent boundary, that is the mid-Atlantic ridge, they have found that this has the youngest this crust is the youngest, this whole crust. Similarly over here also, which is another divergent boundary, so the age of this crust is the youngest. So along all the divergent boundary that present on the globe, they identified that they are the youngest crust. So that phenomena supported this seafloor spreading uh, event. And if we look into some key features of this particular mid-Atlantic ridge, is that it forms the 16-kilometer long submerged mountain range. So sometimes you can see that whole, like, since the length of this boundary is a pretty large, You can see that from this end, it is going up to the other end. So due to which we observe that it has a 16,000 kilometer long submerged mountain range. Because during the upwelling of this mantle, it forms the mountain kind of features, and we called it as a submerged mountain feature. And sometimes this feature could be so much high that you can see the evidence of this on the island as well, and this first exposed in the Iceland. So this submerged mountains was first exposed on the island Iceland zone. Now moving to the another question. So I hope now you can answer questions related to this seafloor spreading and what is this mid-Atlantic ridge and what is this convergent boundary ring of fire. I hope all of things are clear to everyone. Moving forward to the second question that I have taken for this session is this, that the boundaries between magnetic bands are contours of equal age are called. So if we try to solve this question further, so for that we first need to understand two keywords that are present in this question. First is the magnetic bands, okay, and second is the equal age. So these two are the key features to address this question. Apart from that, we also understand each and every option and what each term signifies, like what is isosesmal, what is isobar, what is isothermal, and what is isochrome. So first, let's understand what are these magnetic belts, because we haven't discussed it so far. So to understand the magnetic bends, it is the continuation of the seafloor spreading that we have just now discussed. So in this magnetic bends, so as we discussed earlier, that this mantle plume get evolved and come to the seafloor. And here you can see this is the newly formed crust. And since the axis is at the center of this newly formed crust, and that's why we called it as the mid sorry mid oceanic ridge. Okay. Now, what happens that this the seafloor spreading or mid-oceanic ridge phenomena uh, is supported by the three theories. First is the high heat flow. That is obvious that when the mantle come at the sea floor or on the surface, definitely you'll get the high heat flow on that particular region. Second feature that supported this theory is that low seismic velocity. So since it's a hot molten rock, so due to which the seismic velocity gets impeded, and that's why we got a low seismic velocity phenomena along this seafloor spreading zone. And the third one is the magnetic anomalies. So let's understand magnetic anomaly because it is related to the magnetic bands that we want to understand. So, so with this features, with this particular image, we can understand it. So now the magma has come up to the surface and it's started flowing across the axis. Now, what magma contains? We have already discussed that magma, the major composition of magma includes the silicates plus materials and then the magnesium and some amount of manganese as well. So among them, iron and manganese has the magnetic property. And we also know that Earth has its own magnetic field. So due to that, it attains the magnetic field of the Earth. And we also know that there is a reversal in magnetic polarity after every certain time. So suppose here it has the normal magnetic polarity, and when the magnetic polarity gets changed, or after some duration of time, when this reversal happens, we can see that the other layer that deposited during that time, it shows the reversal in polarity. So the one layer is showing and it is symmetric along this axis, that is the mid-oceanic ridge. So this the pattern will be same on both the sides. So if you have here the normal magnetic polarity, so sorry, yeah. So there also on the right hand side also you will get the normal magnetic polarity. Similarly, after that, now we are getting this reversal in polarity that is signified by this white color. So here also on this right hand side and on the left hand side, we can see that there is a reversal in polarity. And now the color of each normal polarity is different because it shows that there is a change in the magnetic intensity, because every time when this polarity change happens, the intensity of the magnetic field is also get fluctuates. So if in a one cycle you are getting the high magnetic polarity, then it's for sure that in the next cycle you will face the low magnetic polarity. Now, to understand it in a more better form, let's move to the another slide. So, I hope with this figure you can clearly understand that how this is happening. So, as I mentioned earlier, that these two plates are going away from each other, and the nature of these two plates are oceanic. So, they both are oceanic plates. And at the center of this, we will get the mid-oceanic ridge or mid-ocean ridge. Through this magma comes to the sea floor and it starts spreading. And since it has started spreading, due to which we can get the magnetic bands. Okay, so these are the magnetic bands that we are getting over here. So first, so there the three colors are indicating that there is a change in magnetic intensity, but this change is that they all are normal magnetic polarity. And for the reversed, the this beige color is showing that there is a reversal in polarity. So the key features, if we want to highlight of this magnetic bands, is that the strength of the geomagnetic field is alternative, anomalously high and low with increasing distance away from the axis of the oceanic ridge system. The anomalous features are nearly symmetrically arranged on both sides of the axis. So we can see that this both sides has shows the same pattern. And the age of or the time that it's gets deposited, it should be same, because it seems logical as well that when this band got solidified and attained this magnetic polarity, so this band would also be solidified and attain the magnetic polarity on the same time. So now we have understood what is the magnetic bands. Okay. Now let's understand what are the terminologies that we have seen in the options. So there were majorly four options. First was the isoseismal. So what this isoseismal indicates that it's relate or denoting the lines of the map connecting the places where the earthquake was experienced with equal strength. So remember, maybe this terminology will help you to address another questions of the exams or the upcoming assignments. So please carefully understand each and every terminology because it will be used frequently. So first is the isoseismal. So isoseismal indicates the region which has the equal strength of the earthquake. that they have experienced. Now, second come to the isobars. So, isobars is a general term. So, it indicates that the lines that represent the constant pressure. And a line drawn on weather map connecting points of equal pressure is called the isobar. Okay. Now, the fourth point is the isothermal. So, what this isothermal indicates? It indicates the region which has the equal equality of the temperature, or the temperature is same. And the fourth one is come the isochrone. And this isochrone is in geology we use it very frequently. So what this isochrone indicates, it indicates a series of rock or minerals that can be assumed to have the same age and identical abundance of their initial isotopic ratio. So on the basis of isotopic ratio, they do the dating, and on the basis of the dating, they identify that like through this isotopic ratio, they do the dating. Now through the dating, they identify what would be the age of that particular rock or mineral that we are looking into. So once identify the dating, we can create a isochrone. So if we go back to the question that we were trying to address, is that now we have equal age. We want to mark the equal age and the magnetic bands. We have understood that magnetic bands would have a symmetry. So the age of this particular band would be same as the age of this particular band. Similarly, age for this particular band would be same as the age of this particular band. And since we are talking about the equal age, so yes, among all these options, this isochrone will be the best choice of answer. I hope you have understood the concept of these questions and would able to answer the questions related or the nearby in this particular concept. Now moving forward, let's understand few another concepts that will again help you to address the other questions of the assignments. So the another phenomena, as I mentioned that in general, like between the oceanic and oceanic plate, we found the divergence boundary. So that is a general phenomena, and due to that divergence, we identify the seafloor spreading, and due to which the mid-oceanic ridge forms. And rest of the things, I hope you know that what are the magnetic bands, how they formed, and like like they are of equal age, that each band uh, and each band would have the same age and the other band would have a different age. Now move to the another concept, that is East African Rift System. So this is the exception because here it happens in the east side of Africa. So that's why it has a name of East African Rift System. So this rifting we have already understood previously, like here. So what happens in rifting? It breaks the continental plate. For example, over here, so at the last stage, what it happened? It break the two plates and form the new plate due to the upwelling motion of the momentum. Okay, so this is the rifting, that the plate gets thinner and thinner and the movement between the plate is diverging, and due to which it gets thinner and thinner over the time. Same phenomena has happened in the East African side, and that's why we call it as a rift system, because here also once like million years back, it was a single entity, like whole African plate was a single entity. But due to this rifting phenomena, what it leads to, it breaks this whole region. Like this got apart from this particular region. And this happened like while creating the triple junction. So this is how this triple junction looks. And that's why this far depression is the triple junction. So if I am to draw, so this would be the afar junction. Okay. Now, so due to which this extra space it has created, like over here, if I change the color, so over here and similarly over here, and the continental part is here. So now, as it was earlier, it was a combined plate, but now it got break into the another plate, and this space is created like this, the two sides, or it forms the two arms. So due to which the first arm formed the Red Sea. Sorry. So first arm formed the Red Sea, and the another side of arm formed the Gulf of Aden. Okay. Now the similar thing you can see on this map of the Africa, where this the dash line like this is showing the developing plate boundary. So here you can see that the newly developed boundary has formed, and so this is the plate that got detached, and because of which this one arm formed the Red Sea over here, and the another arm of this triple junction, because here we can see the three, like the it is meeting the 3 points or three sides. So that's why we are calling it as a triple junction, which in this case is the FR junction. Okay, so this arm form the Red Sea and this another arm form the Gulf of Aden. So I hope all these concepts are clear to all of you, because this is a very crucial concept, and there are the questions in the assignments related to this particular concept. So I hope after this you will be able to answer the questions correctly. Now moving to another concept that I would like to discuss during this session is the hotspots. Now hotspot is another kind of like geological feature that we have all seen, like the Hawaiian hotspot range, and even India also we have a lots of hotspot, like in the Mahanadi Rift Basin, and again there is a Rift Basin, so that is in the Rift Basin. Now, if we go by the definition first to understand the hotspot, so what definition suggests is that is a long-lasting magnetic center rooted in the mantle below the lithosphere. So it acts as a anchor, or you can understand it act as a anchored pipe, which brings, like from this figure, I think you can understand that you can, like, is this is the mantle, like below the lithosphere. Now, due to this, you can understand that suppose there is a pipe, so due to that pipe, and since there is a pressure difference, so this mantle will come as a plume and create a hotspot over here. And the location of this pipe will be fixed or anchored. So it's anchored. Okay, and it forms the hotspot. Now, consider another situation in this scenario. Suppose this plate start moving. Okay, and we know that all the plates we have, they move. Though the speed of movement is very slow. For example, like Pacific plates has the speed of 2 centimeter per year. So this is very slow. But if it is moved and we observe for around 1,000 of years, so definitely we can see the movement change. So if it is fixed and plate is moving, so what will happen when the plate will be here? So you can see the hotspot feature on this location of the plate. And if we go back, so earlier this hotspot that we saw would be the active hotspot when it was in this position. And since it's moving, so these many hotspots have been created on this particular plate. And this is the current one, which is active. Because once it will cross that hotspot location, this will become dormant because now there is no another source for the mental activity or to make it uh, to to make it active through this mental plume. So it will got dormant. And that is why we go to the another point of the definition is that a volcanic complex is built up above the magnetic source forming the volcanic island. So whenever it will be here, it will be active and we will call it as a volcanic island. And what happens is sometimes the upwelling material that comes through this mantle would have the height of 1.5 kilometers. So that's why you can see the island range on the like sea on the sea. You can see up to the sea, and that's why there are the beautiful Hawaii Island and all those islands are formed. So that was the uh, mechanism behind their formation. And once they get extinct and or when the plate moved away from that hotspot, that extinct volcanic island sinks beneath the surface because now there's no active source which will feed that island, and some are truncated by erosion to sea level and become gyots. So when it will be submerged up to the sea level, it will become the gyots. So this phenomena we can another understand through the real example that happened in the Hawaii range. So again, this Hawaii range is in the Pacific plate, which is the active plate. So you can see that. So suppose it is the active. This location is the active location of the hotspot, which is fixed, but since place is moving. So this, hotspot feature also helps us to identify the plate movement because it will provide us the actual movement because once uh, we know that once this hotspot over here which is not active but earlier it was active, so we can identify the difference between that, and this will help us to identify the plate movement. So it will provide us the absolute plate movement. So this is one of the tool or the technique that we have to exactly identify or to accurately estimate the plate movement and also the plate direction. So you can see that the plate motion is happening like this. So first it was going in that direction. That's why we are getting the linear range of the volcanic island over here, but the previous one islands that was the that's why we are using the word sea mounts over here because now they are not the active island, they are just mounts, sea mounts, and their direction was like this. So you can see that plate motion is first was like earlier it was like this and now it is like this. And again also here we can see the same feature that we are seeing in the Hawaii ridge, the linear range of the this volcanic islands. Here in here case because they are dormant for a longer time, so that's why they become the seamounts. But how they validated this theory? It is also again a very interesting thing to know. So that's why I thought of discussing with you. Yeah, so let's move to the part where that how the researchers had confirmed this theory. So, this is how they confirm this hotspot theory that hotspot is an anchored kind of feature, and the plate is moving, and once the plate moved through that location, so that particular volcanic feature got extinct. So what they did, they do the radiometric dating of the linear chains in the Pacific basin, which gives them the almost identical range, and they identify the linear trend. So for the dating, they use the potassium argon aging dating. So they plotted on the y-axis the dating or the age that they got from this dating, and on the x-axis they plotted the distance from the Kailua hotspot, which is the currently active hotspot. So this is the current location of this, or the fixed location of the hotspot. And this Kailua location is present over here as of now. But if we go back to the earlier volcanic complex or the island range that we have seen on the Pacific Ocean, so their age was matching correctly, and through this dating and the age plotting map, they identified that the movement of the plate was around 10 centimeter per year. Earlier, they were estimating that it would be around 10 centimeter per year, but with this hotspot theory, they were able to identify the absolute motion of the Pacific plate. So this is how they proved the hypothesis of the Pacific plate, and also along with that, they were able to identify the plate motion. So you can see that there's a linearly related feature, and they all are the island feature. So that this first observation that they had, and they proved it with the help of this dating versus distance plot, and they confirmed it successfully. So now I think we are done for the today, and I hope you have understood this all the concepts that we have discussed during this course. For example, the hotspot concept and how it got proved. And then after that, we also discussed the East African rift system and how they formed, and what are the like new features that emerged through this rift phenomena. And before that, we discussed the terminologies, like what are the isoseismal, what are the isobars, what is the isothermal and isochrone. And also we have understood the magnetic bands and how they formed, which is with the help of the sea floor spreading they formed, and this is the one evidence to prove that theory. And apart from that, we have understood that what are the divergent boundary, and what are this mid-oceanic ridge, what are the sea floor spreading, and how again they prove the sea floor spreading by plotting the age across all the globe, and they identified the youngest crust are formed across the oceanic ridge or the divergent boundary. And also we have seen that the most active region on this globe is that Pacific range, where this convergent movement is happening between the Pacific plate and the nearby plate, and that's where we are getting lots of trench kind of features and the volcanic along this whole belt, and due to which there are, since they are tectonically active, so they are considered as an unstable zone, and which led to the earthquake activity. So this area particularly faces the highest earthquake rate. And we all know that the famous example of Japan, that Japan is the mostly affected by the earthquakes. And moving further, we have also seen in this session that what are the plates that present on the globe and what kind of boundary they share with the adjacent plate and what are their locations. So all of these things are considered during this lecture, and I hope it would be beneficial for you. And now it will also help you to address the questions related to this week assignments, that is week 3. So have a good evening and see you in the next week.